Okay, this is the 6th video in the curve sketching example problem series. In this video, we're going to sketch this function here. All right, step 1, let's write the domain. So we've got a even root here with just x inside, so we can't input any x that's less than 0, at least when it comes to the square root of x. When it comes to this x minus 3, we can input anything. So that means the domain is going to be from negative infinity to 0, including 0. Or no, the domain will be 0 inclusive to infinity. And the range, what we'll do is let's sketch the graph and we'll come back to the range. All right, intercepts. Y-intercepts, set x equal to 0 and solve for y. Okay, so the origin is an x and a y-intercept. So now let's solve for any other potential x-intercepts other than the origin. Set y equal to 0. All right, so x can equal 3 and x can equal 0. All right, so on the graph, we're going to go from the y-axis from 5 to minus 5, and then from 0 to 6. So 6 to minus 6. But again, the domain, we're not going to be in the negative x region. All right, now and the x-intercepts are x is equal to 3. Okay, the origin, and then x is equal to 3. Now let's check for symmetry. Is this an even function? Well, it's probably, if we can't go into the negative region, it can't be even, I don't believe, but let's just check. Okay, y of minus x is what? Well, yeah, if we're only in the positive region, we can't have any symmetry. As far as symmetry about the y-axis, you could say, well, what about the x-axis? But a function can't be symmetrical about the x-axis, then it's not a function. So this isn't going to have any symmetry, not even any periodicity either. So it's not an even function, not an odd function, it's not periodic. All right, next, let's do the endpoint behavior. So to do the endpoint behavior, you take the limit as x approaches each of the endpoints of the domain. So what is the limit as x approaches 0 from the right of this is equal to what? This is equal to 0. You plug in 0 for x and you get 0. Okay? And you might say, well, what's the point of doing this? Well, you could have like a logarithm. It looks something like this. You know, you could find you have an asymptote. For the log of x, the limit as x approaches 0 from the right of log of x is negative infinity. So you just want to you want to analyze the endpoints this way. Okay, now this infinity what do you get here? Infinity minus 3 is infinity. Square root of infinity is infinity. So you have infinity times infinity. This is equal to infinity. Okay. All right, now let's get the critical points with respect to the first and second derivative. Okay, so we've got x minus 3 times the square root of x. Store this as e. Okay, so now let's take the derivative with respect to x of e. So one critical point is going to be where x is equal to 0. So the first derivative Okay, so we'll have x is equal to 0 because the first derivative doesn't exist there. Well, okay, no, actually, I take it back. That's not a critical point because that's one of the endpoints. So no, that's not a critical point. That's an endpoint. Okay, so let's solve for. So there's no points where the derivative doesn't exist within the domain. That's not an endpoint. So let's solve for when this is equal to 0 for x. X is equal to 1, okay? So x is equal to 1. All right, now if we plug this in, we get what? Minus 2 times 1, so minus 2. All right, now the second derivative, okay, and then if we solve, x is equal to minus 1. Okay. All right. Oh, well, that's outside of the domain. So there are no critical points with respect to the second derivative. So none. So we only have one critical point overall. X is equal to 1. So let's plot this. This is 3, so 0.6, 1.2. So this is about 1. And then minus 2, 0.5, 1, 1.5, 2. Okay, so about right here. Okay. All right, now we could, to look for vertical asymptotes, we would take the limit as x approaches each of the critical points, so from each side. So we take the limit as x approaches 1 from the left and the right and see if it goes to infinity and we have a vertical asymptote. But we know that we can see that this is not going to be a vertical asymptote, have any vertical asymptotes. And also we know this is not a point where the first derivative doesn't exist. This is where the first derivative is equal to 0. So we're going to be continuous everywhere. The first derivative equals 0. This is not going to be an asymptote. So we don't need to check for any vertical asymptotes here. So next, let's get the intervals of the increasing and decreasing intervals. So we're just going to have one potential point where the first derivative changes signs at x is equal to 1. Okay, so let's check and see if we get the first derivative. Okay, and now with x equal to 0, it's undefined, so no, no. Okay, x is equal to 0.5, it's negative, so decreasing. All right, now with x equal to 2, it's positive, so it's increasing. Okay, now then for concavity, there are no points where the concavity changes, so it's going to have one concavity throughout the entire domain. That's everything's to the left of 0, to the right of 0. So it's undefined here, and then to the okay, x, okay, and then we want to check this for when x is equal to, let's say, 2, whatever, concave up. Okay, now this is not a discontinuity, and so because of that, we can use the first derivative test to see that we go from decreasing to increasing. The first derivative changes signs, so this is a local min. Okay, and then we have no inflection points. There's no critical points with respect to the second derivative. Okay, so now let's sketch the curve. This is going to be a local min, so the slope is 0, and then okay, so we would expect it to do something like that, and then it just stays concave up. it just goes through this point here. There's no, this is the only point where something special happens here. The slope is 0, it's the local min. Everywhere else, there's no inflection points. There's nothing unique happening. So we're just going to go through this point and go off. Okay, like that. And so does this make sense? Well, all right, the limit as x approaches 0 from the right of the function is it's going to 0. That's right. There's no vertical slopes or anything. There's no unique slopes. And then, okay, from here, we're concave up and the function is decreasing until we get to 1. Okay? Concave up, function decreasing until we get to 1. Then we've got a local min, slope 0. After that, the function is increasing. That's what we found. And we just remain concave up. As x goes to infinity, the function approaches infinity, and we remain concave up to infinity. So there you go. That's it. Okay, now coming back to the range, based on the graph we drew, what can we see as the range? Well, the range is going to be -2 to infinity, right? There's no value of x that you can input to where you'll get a y that's less than minus 2. But you can get any other potential y. So the range is -2 to infinity.